deliver a reset. So these are, and the programming interface for, but about the programming interface in a moment. Still, if we implement a microcontroller into a physical device, into a PCB and want to integrate it with the circuitry around, then we must take it into account the structure of the I/O ports, because the I/O ports are the places where we connect anything. So, what is the characteristic of the I/O port and how they are constructed? Because in case of microcontrollers, they consist of a few elements. It's from some, I don't know which microcontroller to be honest, but it doesn't matter. It's common. This schematic is common to all microcontrollers, so to greatest majority. So I had there are some microcontrollers with a bit different schematics, but in general they share the functionality and they share they share the majority of the components that you can see here on the slide. So this is the schematic of one pin. Of just one pin. I think we started it previously, if I'm not mistaken, but it was so long time ago that I will just repeat. So if we started, then I will repeat it a bit, so that there is no omission here, because it's the knowledge of the structure of the port is important from practical point of view. So first of all, in case of the I/O pin, we've got, here is the hardware, so here is the physical pin, here is the internals of the microcontroller, so various registers, because the port is generally a peripheral. It's generally peripheral because if you take a look from the microcontroller's point of view, there is a microprocessor and a port. Port is usually a peripheral with dedicated registers, with dedicated functionality, and with dedicated behavior. So from the microcontroller's point of view, we've got a couple of registers. Usually we've got, the major are two registers, and they are always present in any microcontroller. So the register which is used for writing something to the port and from reading something from a port, this is register number one. And the second register there is always is the register that tells us, or the register where we can define the directivity of the port. So if the port is input or if the port is output. So these are the two registers which are always present for reading, writing to port, and for changing the direction of the registers. There are sometimes more registers present, like changing the drive strength, driving the pull-ups, pull-downs, switching on some alternate functionality, but this is optional. So it's not, those registers are differ from microcontroller to microcontroller, but those two registers for setting the writing and reading from, and for setting the directivity are always present. Why do we need to set the directivity? This comes from the fact that the input, so some input buffers, so this is the input power, input driver, so the impedance of the input driver is very high, Y should be infinite, while the output driver, the impedance should be zero. So perfect output driver should have no impedance at all. Then it would theoretically be possible to drive with this output driver infinite loads, infinitesimally small loads, large loads. So that require a lot of power. In reality, of course, neither this has infinite resist impedance, nor this has zero impedance. So here the impedance usually goes into megaohms, so it's 10 to 7 usually, so a few megaohms at least. Usually with capacitance with a few picofarads. That's usually the parameter of this part of the input driver. While the output driver, the parameters that you can expect from a microcontroller is around 10 to 100 ohm. This is the serial resistance, which means that the load, so how much current we can drain from the port, usually we can drain between 1 and 100 milliamps, although the usual value is about 10 milliamps. That's something that you can drive from a microcontroller. What does it mean? It does mean that you can connect to an output port any number of inputs, almost any number of inputs. That's not that obvious I would say that's I'm pointing out, I'm stressing this out, that we can connect any number of inputs, because in the classic TTL logic, we talked about it a bit during introduction to microcontrollers. In classic TTL logic, there was a limit about 10 inputs to one output. So if you wanted to connect one gate to one output from a NAND gate, NOR gate, whatever gate we wanted, to other gates, then no more than 10, that was the limitation, because the standard TTL was capable of driving just 0.4 milliamp or something like this. This was the standard TTL strength. It was so weak. Today, we talk here about that standard, we have CMOS, and those transistor output stage is usually quite strong, unless you take very ancient microcontroller in your design. But normally we talk about 10 milliamps, 20 milliamps, sometimes even 100, but be careful here, 100 is not always possible, so it's quite rare. Normally we have 10 milliamps, but still, if we take into account that we need a couple of microamps to drive one input, then it means that we can connect any number of inputs any number of inputs to one output. What is limiting? That's a good question to you then. Okay, the current is not limiting us, but still, from practical point of view, it's not very practical to connect any number of inputs to, or very large number of inputs to one output. Why? It is not practical. It's not limited by the impedance. But what is limiting us? The number of connections.
Input capacitance?
Yes, of course. Because if we connect too many inputs here, if we the capacitance naturally will add, because parallel connection means that we simply add the capacitance. So 3 picoamps plus 3 picoamps plus 3 picoamps plus 3 picoamps, then we'll end up with 100 picofarads, of course. Then we'll end up with hundreds of picofarads. We may end up. And this will limit the speed, the transition speed. So of course the transition will be slower. So then instead of a nice square wave, we can expect a triangular wave or something like this for fast switching. So that's the limit in case of connection. So that's why we usually don't connect 100 or something like this inputs to one output. What this 10 milliamps gives us, because it's still a pretty decent current also if we want to connect some load. From practical point of view, for example, you can connect directly an LED. You can try to drive a relay switch out of it. Of course, you can also try to connect it, mind that you may try to use, of course, from microcontroller point of view, there is no problem. You can connect an LED. 10 milliamps, you can see the LED. Of course, they will not be as strong to make bright in the room. So it's not that. So such LEDs require an amp or something like this. But for small LED and SMT case, no problem. If you want to have more current, it's very good idea to use the MOSFET, simple MOSFET. Then you can drive LED that needs amps of current. For example, LV or some motor or something like this. This 10 milliamps is sufficient really to drive here even 10 amps, I would say. Even more. But again, what's the problem of driving too high loads directly from this output? What's the problem? What may be the disadvantage? So for example, if you try to drive 100 amps or something like this.
The gate capacitance?
Yeah, the problem is the gate capacitance. The problem is that, remember about it, so don't forget about it, that the current here is flowing only during switching the transistor on and switching it off. Then we need the current. So then the capacity, because this is physically a capacitor. So we have to charge the capacitor, and 10 milliamps is not sufficient to drive too heavy loads, but still pretty decent values we can expect. Here we have a protection. We talked about it, I think, if I'm not mistaken, previously. So we have this protection diodes. That's why from maximum limits, if you read the maximum limits table in microcontroller, there is a VDD plus 0.2 and VDD VSS minus 0.2, which is the maximum voltage. Because this is 0.2, 0.3, 0.5, depends on the microcontroller. This is the threshold voltage for the forward voltage of these diodes. Because take a look, if there is a protection, if we exceed this junction voltage here, then the current starts to flow either here or here. If the current is limited, so we talk here about the clamp current. This is the clamp current of this diode. So if we limit the current flowing in or out of this I/O pin, then the diodes will protect the internals of the microcontrollers, but they will not evaporate. But if we don't limit the current and we connect minus 12 volts, for example, or plus 12 volts here, then either of those diodes will simply explode internally. It will damage, making a short circuit here or a short circuit here, and that's what's happening. So if you exceed with the input-output voltage and you don't take care about the clamping current, so if you don't limit the clamping current to series resistor, either of these diodes will simply will break, and causing the whole functionality to be brought to be the whole pin of the port to be infunctional. And that's what's happening. If you damaging the microcontroller is usually about damaging this protection diodes. So very often we've got this port functional if we exceed with the voltage, but we break down this current, this diodes. So that's actually what's happening. That's what you can expect. Then how you can observe it? Then because this part is heating. Of course, the whole microcontroller starts to heat because there is a current flowing here or here. Or somewhere here there is flowing current even with no signal connected. When you break the microcontroller, when you break the pin. A bit important roles or important sometimes are the pull-ups and pull-downs. Microcontrollers usually have pull-ups. It's much more rare to have the pull-downs. It's really limited to some limited families which have pull-downs. Usually we just have pull-ups. Why do we need pull-ups? Of course, for wired OR. It is called the wired OR functionality, so that we combine many outputs on one line. Because normally we shouldn't connect many outputs to one line, push-pull outputs, because they have different impedances and we shouldn't connect them together. But if we have a pull-up configuration, if we have an open, so-called open drain configuration, open collector configuration, so when this transistor is missing and we have just one pull-up, then we can combine many outputs onto one line, and then there is no problem with current flow and with various impedances. And for this functionality, we need a pull-up. For open drain functionality, we usually have the pull-up externally, but in some applications, internal pull-up makes it working. What else can we see here? The input buffer. So let's check the input driver. In case of input driver, we've got such a buffer with hysteresis. This buffer is used to get rid of analog noises a bit. So the hysteresis level is usually set to pretty low values, but we've got this input stage, but it's still tens of millivolts, non-regulated usually, and we can, thanks to this small noises at the input are not harmful to the digital electronics. Still, we have in some microcontrollers special analog inputs. Of course, the analog input is connected directly to the I/O pin. Then, if we want to use analog input, then this buffer is simply put in the off state and in high impedance so that it does not disturb the analog functionality. Analog may be analog to digital converter, maybe op-amp, maybe comparator, analog comparator. So this kind of functionality we can find as connected here. Yeah, I think that's it. About the ports, the major parameters of the port we can always find in a dedicated table. In this dedicated table, what is interesting that can be read, first of all, the values of that are accepted at the input. Then we have always the values that we can expect that will be present at the output. And here we can see the load of each microcontroller, of course, has it a bit differently. Here we can read that, for example, if you supply it from 5 volts, you can try to drain 20 milliamps out of this microcontroller, which means that you can use the stronger LED, for example. Also, sometimes important parameter is the leakage. The leakage, that's of course the impedance of this buffer, Schmitt trigger buffer, because that's sometimes analog part, but the analog has usually higher impedance than this Schmitt trigger. That's how technologically it is done. And so the main source of leakage is usually this buffer. This is of course important if we talk about very low power consumption devices. Then this 1 microamp may, this is not negligible, to be honest, because it's flowing always. So sometimes, and especially if you have connected tens or hundreds of ports, then just 1 microamp can give us very substantial power drain. And the last parameter that you can see here in the table, various versions of the pull-ups, internal pull-ups, what are the values? Not very precise pull-ups and the weak pull-ups, because normally our external we use pull-ups 4.7, 2.2, 10K. Here very weak pull-ups, but still very nice extension. Pull-downs, if we talk about the pull-downs, so those values, they are similar values. They usually you can expect as well tens of milliamps, tens of kilo ohms. Here not very precise values, so like here that we have the something between 20 and 30 and 60 that we can expect here. Here's for STM8 to have greater details. So this is the schematic of the taken from the STM8 documentation. That's how it looks in the STM8, and we've got almost all the elements that were presented, that were shown on the previous slide. So we've got the pin here as well, the protection diodes. So they are necessary. So they always exist in microcontrollers because we have CMOS transistors and they don't like ESD. So we've got this protection diodes to protect against ESD. Then we've got some pull-up, no pull-down here, as you can see. The Schmitt trigger with the analog input somewhere here. And there is the important stuff, the registers that are necessary for servicing the port itself. And then from this slide you can read that the data register is the data direction register. So the register set for changing the direction is the data direction DDR in this microcontroller. So if you want to modify the pin to be input or output, then you have to change the DDR register, so the appropriate bit in the DDR register. For outputting data, we've got a dedicated ODR, output data register, and for reading, we've got the input data register. Here in this microcontroller, different names, but that's not always. Sometimes microcontrollers have common port that you can read or write. If you read, you read from this pin, and if you write to this pin. But it's visible from programmer's model. It's visible as one port. Here in this microcontroller, 2 dedicated ports: output data register, input data register, and what we can expect 2 configuration registers in this microcontroller. So CR1 and CR2, where we have all these gates regulated. So to give you more. To give you, of course, not to guess, because we can read the functionality from these gates, but no time for it, no sense. Very important table. So the table that is always available in a documentation somewhere, in some part of the documentation, in any microcontroller table, summarizing how to set the port to get the functionality that we need. And here we have the bits. So data direction register bit, CR1 bit and CR2 bit. These registers, each bit means setting for one port, for one physical pin in a port. And take a look what functionality can we configure with those 3 registers or the appropriate bits in the register. So if we want to modify the port, the bit 0 in a port, there will be data direction register bit 0, CR1 register bit 0, and CR2 register bit 0 had to be modified. So for input standard 1, we've got data, the DDR is always 0. For output, DDR is always 1. And that's common. Microcontrollers, it's easy to memorize. So output is 1 and input is 0. So it's reverse. So if you take the letters, I don't know why, but it's always there. So input, because input is 0 and output is 1. It's always this way. I don't know why. Why couldn't it be 1 and 1, 0 and 0? It's about setting. But every microcontroller I know, or at least, yeah, that I know is having something like this. So it's easy to remember 1, 0 and 0, 1. So we have got input and output functionality. Then in case of input, we've got a couple of options here. So namely 4 options. So 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, and 1, 1. The standard input is floating without interrupt. That's the input that's the standard input. So no pull up, no pull down is there, and no interrupt is being serviced, because in this microcontroller we have a possibility to service interrupts directly. It's not, yeah, here it is. So interrupt, which means that we can service if anything changes on the pin. So if there is a rising or falling edge, then we can have an information to an interrupt, and then we can interrupt service routine can start. Then we've got a pull up. Pull up, it's not necessary for inputs, but pull up we use when we want to be sure that if nothing is connected to the line, that the line is in a high state, in a logically high state. So that's the 1-0 configuration, and then we have appropriate 0-1 and 1-1 with interrupt being switched on. That's not standard, yeah?
So is there interrupt vector for every pin or for port?
For port.
Okay.
That's for port. So it's again, it's different for different microcontrollers. It's done in a different way. In case of this external interrupts, because sometimes we've got there must be some aggregation. So there are too many pins. Maybe even starting earlier. In earlier microcontrollers, so in the old ones, sometimes they're still in the market. There are dedicated external interrupt pins, dedicated ones, 1, 2, 3 external interrupt pins, and then in such a case, every pin has its dedicated interrupt, because there are 2, 3, 4 pins with this functionality. Today, the microcontrollers, and STM8 is an example. We've got any pin can generate an interrupt. That's very convenient, because then we make a PCB. It's easier to make a PCB because then we can connect a signal to any pin in a microcontroller that we have left, that is easy to be connected, and then we can, only in software, we can configure which pin will generate the interrupt. But then, of course, it's completely impractical that the pin, each pin has a dedicated vector, interrupt vector. So we have some aggregation. So there is a multiplexer that multiplexes the pins, and here it comes in depending on the microcontroller. Sometimes there is one port, one interrupt. So we have a multiplexer that multiplexes the pins to one interrupt. Sometimes we have a bit different model that each pin number is aggregated from any port. Pins with pins 0 are aggregated into one interrupt, pins 1 are aggregated in another one. So port A pin 0, port B pin 0, port C pin 0, and so on, aggregated into one interrupt, and ports 1 into another interrupt, so on. So there is some aggregation. Not that one pin, one interrupt, but still we can configure it. In case of output, we've got, of course, DDR as 1. But then, depending on the configuration of the CR1 and CR2 pin bits, we have either the standard push-pull output, so this is 1-0. Then we've got the open drain and open drain with fast mode. So push-pull is also fast mode or standard. What's the difference between fast mode and standard one? Who knows? Who has had an experience with this? Fast output and standard output. What's the difference?
Drive strength.
Yes, that's not exactly the drive strength. But it's connected with the drive strength. But it's not exactly. It's about capacitance, the output capacitance, or the slew rate, because it's not the drive strength, but it's about the slew rate of the output. So the slew rate is limited because drive strength is slightly different thing. We may have slow port with high drive strength and slow port with low drive strength. Fast and slow port differs that the output, the shape of the output is for fast is this one, for slow is this one. That's the fast mode. So this is fast, this is fast, this is slow. What's the sense of that fast and slow? So theoretically you could say, yeah, let's just use fast and that's it. So fast is better because we can have faster clocking. The problem, unfortunately, with fast mode is that if we change it to, if we make a Fourier transform of this fast switching, we'll end up with high bandwidth of noises coming from this fast switching, which means that these fast noises are propagating very nicely into another tracks or paths or pins, because this generates an impulse of wide bandwidth. That's why, unless we need very slow, we need to switch into megahertz or higher frequency. So for low switching, for 10 kilohertz and below, it's better always to switch to slow. So the default is slow, and that's also my remark, that it's always better to choose by default slow, because if you want to blink an LED, there is no sense of blinking it in a fast mode, because it will just generate unnecessary noise and will give you no additional improvement in case of functioning. So by default, it's always better to choose a slow version, either open drain. Push-pull fast mode is open drain fast mode honestly has very little sense. Because with push-pull, the functioning of the transistor, this option has no sense, in my opinion, because it is very good optimization. So, maybe let's not go into this detail because we don't have time for everything. But actually, don't switch on this option. Maybe let's put it short. So if you want some explanation, let me know. I'll give you the explanation why this option has no sense. But if you want open drain, don't count on, maybe this way. If you want open drain functionality, don't count on megahertz. 100 of kilohertz in open drain is really 100, 500 kilohertz is a really good speed. If you want to switch with megahertz switching, push-pull, because open drain is really sensitive to the resistance, to the pull-up resistance. So we don't have time for it. Again, if you have any questions about this, I'm open. The last thing, flash programming. We always have to connect some interface for accessing the memory of the microcontroller. Always. Today, there are no microcontrollers which are programmable outside of the system, which is good actually. So every microcontroller on the market that we can find today have so-called in-system programmability function. So it is called ISP, system programming. It became so common that today it's difficult to find a microcontroller without this functionality. So almost all microcontrollers on the market have the flash memory, and if they have flash memory, we can access the flash memory through the programming interface. So we must think about using the flash, about adding some programming interface. In the past, there used to be a couple of solutions for programming a microcontroller. One of the common solutions was the UART interface. UART was very popular, and in 20 years ago, the UART was the standard method of programming the microcontroller. The problem with UART, so the good thing about the UART was that it was simple. That was good. It did not require any special, almost any special setup, because the computers 20 years ago, they all had UART interface. So even the laptops, but of course the stationary standard computers, they all as well included 1-2 ports sometimes of UART, of RS-232. Today it's not that obvious, so today we've got USB. And today the microcontrollers, it's possible to program the microcontrollers over USB, which is also very nice. Because we can program, for example, the STM8, not really, at least I don't know. Maybe the very newest one. I'm not tracing securely the STM8 market. But STM32s, for example, you can switch into UART programmability mode, and then you just switch it into this boot mode with USB, and then you connect USB cable, and here it is, and here it's enough. So then you can program it directly through the USB. In case of, but that's for programming. Today, programming is not enough. Today, the second problem when you want to play, when you want to work with microcontrollers, is to have access to the registers. So to go a step further and beyond the programming, to access also the registers and to make a debugging. For debugging, the standard interface in the industry is so-called JTAG interface. This semester we'll not have time for this, but maybe next semester. If not, then maybe during Master of Science course, if you enroll in this course, I compared the JTAG. We talk about the JTAG and the functionality of the JTAG interface, because this is not only for microcontrollers, it's an interface used in the electronic industry for accessing various kinds of devices. This interface, the problem is that it's a bit slow and a bit complicated and a bit expensive. I remember the times where programming, so having a board with UART interface, so adapting UART interface just for programming, cost no zloty, no euro, because it was just connecting to a computer and then running a free of charge software to program. But then if you wanted a debugging, only JTAG was the only option, and the JTAG interface cost was about 200-300 euros, plus dedicated software for the JTAG communication, which additional few hundred euros required. So that was the difference. Zero cost, no cost UART programming, or very high cost or high cost JTAG debugging. Today we have fortunately various interfaces like SWD, SWIM interfaces that we can use for programming and for debugging, for accessing the internals of the microcontrollers. And if we consider a new PCB board, it is a very good idea to use their not only interface for programming, but also to use an interface for debugging, even if it requires some additional hardware, which is the case for these sample interfaces. They require some basic electronics that you can buy on AliExpress for a few dollars, for a few euro today. So it's still much more affordable than JTAG, but gives you the access to the registers, which is not accessible through the standard UART or various programmers that we have, simple interfaces that we have in standard old ancient, I would say even microcontrollers. Those interfaces maybe we'll not analyze them today because there is no neither time nor sense to analyze them now, the debugging. Let's go with something simpler. But I would like just to point out, because this is the example in STM8, how does it look inside the structure. So if we want this, here is SWIM pin, not SMIM, but SWIM, should be W, swim pin. In general, there is a whole structure for servicing this debugging communication. Of course, this is hidden inside, and thanks to this, it's very easy to access it. Take a look. The communication, the communication is pretty simple. So it's just a single pin communication with some timing defined and some comments defined. Of course, even if we are skilled enough, we can try to communicate to this part by ourselves, even if we don't want to pay somebody for doing this, because the pieces of hardware that you can buy on AliExpress or Allegro, eBay, whatever you want to buy, they are pretty cheap. But even if you don't want to pay anybody for this, you can still make SWIM or SWD, for example, by yourself. There is a lot of documentation about accessing this module, and from this module then, and from this debug module, because actually we are accessing this part, we can access the peripherals, we can access RAM, we can access flash, we can access the core itself. So which means that we can program the flash. Of course, that's the basic functionality, but we can monitor what is happening inside. In general, then debugging is something that seems very trivial because we just connect the programmer, we connect the cable, and it's done, it's working. But in practice, there is a whole structure inside supporting this simple communication that for us is simple, but in fact, a lot of communication is going on here, giving us the access to all the peripherals and all the memories and the core itself inside the microcontroller. We will stop there. We will stop there. Again, maybe we have time next semester for this. If not, then of course you always can come and we can analyze that functionality if you're interested. Good. Let's go further. Let's go further. That would be about the basic electrical peripherals. And now let's move towards peripherals. Let me open. Peripherals. What are the basic peripherals besides memory in microcontrollers and ports that we already talked about? That's the next in the on the list are timers and interrupts, and that's the major. These are the heroes of today. The next heroes besides the ports, timers, and then the interrupts. Timers, something really simple. At least it used to be something that counts time. Naturally, we can use a microcontroller with ports to do this, because microcontroller is clocked with a certain clocking speed, and if it is clocked with a certain clocking speed, we can count, we can check use knobs or do something in software to count something, to monitor the inputs, to generate the output in a timely manner, to generate a time base with a microcontroller. Of course, we can do it, but this is so simple that there is absolutely no sense of using processing power of the CPU itself to do such a stupid stuff like counting pulses, like generating some repetitive signal or generating a time base. For this purpose, the people have integrated the timers, the timer blocks, the timer peripherals into the structure of the microcontrollers. And again, the history shows how important it is. I remember the 8051, we'll talk about it in the second part of the semester at least a bit. I will show you the historical, because this is the ancestor of the microcontrollers today, so the 8051 and 8052. And in this microcontrollers dated beginning of 1980s, there were two timers, just two timers. Today, in microcontrollers, we've got about 20. That's the difference. There were two timers, there were 8-bit timers. One timer was for wide use, for universal use, and one timer was for the communication interface. Today we've got 20 timers that can work independently or can be synchronized with each other. So this is very important today, and we really use many timers. Major functionality of the timers we have in microcontroller. Generating time base, that's functionality number one. Time base or time bases for the events that we are servicing in the microcontrollers. Capturing external events, also capturing internal events, because external means here external to the timer, but not exactly external to the microcontroller. So they can be events coming from the external world that, I don't know, one pin is changed, the state of the pin is changed, or some communication started, but it can be capturing when, for example, some peripheral finished the operation, and we can measure some operation on some other peripheral. So some communication started or some communication was finished and we want to measure how much time did it take, we can capture this part. We can measure period between events, so it's very much connected, but still it's a bit different functionality. We can generate PWM signals, so PWM is of course pulse with modulated signals, but not also PWM, but also PDM signals we can generate. So pulse density modulation, this kind of signals we can generate, and various single shot we can generate here as well. In case of microcontrollers, because we've got many timers available, usually we can find in a documentation this kind of table. Because the functionality of the microcontroller timers differ. Usually in microcontrollers the timers are not symmetric, so we have various timers with various functionalities available. Here is an example from STM8, so just 6 timers for one of STM8, but yeah, the list can go on really long. So as I mentioned, today microcontrollers tend to have about 20 timers with varying functionality. So just to have put an attention to something, so it's not possible for us to analyze any possibility that exists on the market. Let's analyze this table in case of STM8. What we can see here, we've got here in this table 6 timers. 1 is advanced, 4 are three are general purpose, and 2 are basic timers. Yeah, we need timers for different functionalities, so there is no need, and the manufacturers are delivering it this way, so that they don't deliver every timer as the advanced super duper timers. So they always decide to reduce the functionality a bit and deliver simpler timers, and that's the case we have here. Out of these timers, 4 are 16-bit. Yeah. 4 are 16-bit and 2 are 8-bit timers. This is 8-bit microcontroller. Therefore, we've got 8-bit timers, but 8-bit timers in general it's something that we should avoid. I wanted to use some stronger word. Why we should avoid the 8-bit timers already after the break. So let's have a 15-minute break. They are very, very short from practical point of view, so they are very, very short, and if you start using them, actually you must really be very careful about overflowing, so about having them, about them counting beyond the range. We can, although sometimes the 8-bit timers have a bit of sense if we use a pre-scaling factor, so if we use a pre-scale. So today it's quite common that the timers have a pre-scaler of the main clock with artificially extending the resolution or the range of operation of such a timer. Because what does it mean, pre-scaler? It means that if we have a pre-scaler, if we set a pre-scaler with of 128, it means that the input has to be input is divided, the frequency of the input signal is divided by the pre-scaler, by the value of the pre-scaler. In case of this microcontroller, even the pre-scalers are limited. Let's take a look for the most advanced Team 1 timer. The pre-scaler, not only the timer is 16-bit, but also the pre-scaler is 16-bit. Which means that theoretically the timer is pseudo 32-bit, because it's not fully 32-bit, it's a pseudo 32-bit. Still, the resolution is a bit extended. In case of the Team 2, 3, and 5 here, we can expect 32-bit, 32,000, which is the prescaler by 15-bit prescaler, and the weakest one, so Team 4 and Team 6, just 7-bit prescaler. So theoretically, it's pseudo 15-bit, better than nothing, but not really something super extra. And then another feature of the counters is if they can count bidirectionally or just in one direction. Again, a very simple functionality. In larger microcontrollers, the timers are by default up-down. Here in this small microcontroller, that's what you can be afraid of in case of microcontrollers with 8-bit CPUs. We may have such queer options like just up-counting timers, but still, here it is. So just one timer is able to count up and down. The other ones are just up counters. We, in case of microcontrollers, quite often have capture/compare channels. Compare, these are for capturing the events, the signals coming from that are present on the pins, and or comparing the main counter with some values, with some preset values. It means that we have usually compare channels, means that we have dedicated registers available besides the main counting register inside the structure. As well, the number of compare channels may differ and usually differs. Here, the simplest one, the 8-bit ones, have no possibility of capture compare functionality. Same is with the outputs. So we have no, here is the complementary outputs, because from the timer they can generate the signal. So not all the timers are able to generate the signal. What's the use of these timers? Yeah, we can read the values, they can generate the interrupts, but they are not able to generate the output signal. Yeah, the repetition counter is the feature that is, just here, so maybe it's not so important. External trigger input, also a feature for starting some counting, for example, so some functionality about this in a moment. Also possibilities of synchronization between the timers. Also such possibilities maybe not important at this stage, but the possibility that exists and is useful sometimes. Important thing is to, besides this is the structure. That's how it looks like inside. That's for timer 1. The other timers have it simplified. So we have normally in timers the time-based unit where the main clock, which is incoming to the timer, goes through this prescaler and then is counted by the counter. So this is team 1, so this is up-down counter, but in case of the simpler timers, we've got just the up functionality, the up counting functionality. Standard feature is the so-called auto reload timer, so that we can set a value here in this register, and whenever this register either comes to the overflow, so for example, it works this way, the auto reload, that we've got the counter register, and let's say it comes up, so it starts from 0FF, it is, and it comes up to of course to FFFF. When it reaches the FFFF and there is a next clock coming in, then instead of going to 000, we can set the auto reload functionality. So there is the auto reload register, so there are various names, and so instead of putting into the counter the value FF00, there is put the value from the auto reload register. So from FFF goes to auto reload, which means that we can put here, we can shorten the counter. So the counter doesn't need to count all the time to 65,535, but it can from 0, but it can count from some value. Also, we can count down. So we can count, if we choose the in the timer 1, we can count, for example, from 100 to 0, and then back to 100. If we put with this 100 into auto reload register. So this is very basic functionality of the timer. That's how we shorten the timer or make it for us convenient to use. So we don't need to count from 0 to 65,000 all the time. So we can shorten the timer, either counting up or down. In case of timer 1, for timers 2 to 6, in STM8 we don't have such functionality because they are always counting up. But you can see why counting down is so nice, for example, for such application, because it's very easy. Then we count from 100 to 0, or from 1,000 to 0, or from 2,000 to 0, whatever we want. Here, important usually, and sometimes the element that gives us some questions is the value of the CKPSC here. So this clocking. That's in some microcontrollers it's not always so clear about the name can vary, but it is more about the value of this signal and about the signal itself. So the input of the main clock, the input to the prescaler. Sometimes it's not such an easy task to find what's the frequency, to be honest. Because the frequency, theoretically, we've got the CPU clocking, which is, let's say, 20 megahertz, because the CPU is the main clock. And if you have a crystal oscillator, let's say 16 megahertz, then the CPU is clocked at 16 megahertz. But it's not always that the timer or timers are clocked from out of the same clocking, out of the same clock or the same clocking frequency. I would say even more than usually the clock PSC. So this clock input is different from CPU. From the F CPU very often. So this is usually the case. Sometimes we can make it even, but quite often the timers are clocked at different clocking, and finding how is it clocked requires sometimes an analysis. It's not always that readable, to be honest, and sometimes even I lose a few minutes to find the frequency that is the input to the prescaler. Of course, that depending on the setting of the prescaler, the C counted here, this signal CK, and T may be different. This is important. This knowledge is really important, because then all this operation, and besides the generating of the time base, because we don't need to use this capture compare array, we can use just this unit. It's not shown here, but we can generate interrupts out of this. For example, an interrupt when it gets down to 0, and we can generate an interrupt then, having a time base. But we have to know that one clock cycle is, for example, 1 millisecond. So this is an important information, and not, for example, 1.024 millisecond, because of course, as a time base, it's useless, because then something will malfunction in our microcontroller. Then we've got this capture compare array, which is additional functionality, because this is the basic one. And this is the additional functionality where we have, first of all, counting of the input, observing of the input signals. So we've got actually here 3 functionalities, to be honest, with this capture and compare array. First functionality is maybe not left and right, but the middle. Because in the middle we've got this compare registers. Compare registers, if they are available, because as you can see here in this table, for example, here and here they are not available. We've got the compare registers where we can put some values, and if the timer counter, if this main counting register, CNT usually it's the name, if this register reaches this value, then an interrupt is generated. Or this value interrupt is generated, or this value interrupt is generated, which means that we can, if we have this kind of functionality, we can generate an interrupt. For example, here, that's the counter value, and the auto reload. So it means that when we overflow, so the counter comes up, overflow comes up, overflow, and so on. But we can generate an interrupt at the overflow, but we can generate an interrupt at certain thresholds. These thresholds are actually set in this compare register. So this is functionality number 1 of this capture and compare. Of course, it works in both directions, so we can have up functionality, down functionality. We can change the direction. It's also possible that the counter works in such an operating mode that it comes up, down, up, down. That's functionality, first functionality of this capture block. Second functionality is that we've got this pin, we use this input stage, and we use these pins, and we can either count how many times here something happens. So we connect here, for example, some source of clocking signal. Of course, not megahertz, but usually much slower. For example, we can count passengers coming in some bus, let's say. And every time a passenger comes in or crosses some line, then we have one pulse here. And then we count these pulses. We can prescale it down. We don't need to. We count these pulses. That's one functionality. Another functionality is we can measure period between something happens. That's also possible through using this input stage and this registers. In this register, then we've got the difference, not how many times something happened, but how often something happened. So when was the last, so actually this is, we've got a snapshot of this value, because that's how it works. So then if a pulse happens here, then we've got a snapshot of the counter, up-down counter, and then we can, in the interrupt, analyze how much time did it take between two occurrences of the second. That's the functionality of the major functionality. In case of the output stage, this is the part 3 of the functionality of the timer, of this capture compare array. It's naturally for generating mainly the PWM, because this is the major functionality to generate the pulse width modulation. So the impulse, pulse width modulation is the best, is the major signals where we use to drive heavy loads. Why is that so? I think you should be aware of. If we have a CMOS, a heavy load, let's say, let's consider we've got a DC motor, maybe the simple stuff, so plus 48 volts, let's say. Then we've got the motor, and we want to drive this motor. So we use a MOSFET. Here it goes to the to microcontroller. Theoretically, that's it. So we can of course make it this way that we can switch the motor on, then it starts rotating, and so we can switch on the transistor, we can switch off the transistor. So the motor either will have a full force, a full torque, or no torque at all, because we just switch it on and off and make the current flowing or not. But of course this is just a functionality of 0-1, so either working or not working at all. Sometimes it's okay, but quite often we need to drive such loads that we would like to have it linear drive, not just 0-1, but that we can drive the torque or the RPMs, the rotations, in a more or less fluent way. And then how we do it with switching, with fast switching on and on. So that we change the width of the pulses, and depending on the duty cycle of the signal, we are driving the motor with the torque at certain, for example, the motor with a torque of at a certain level. Why don't we use the transistor in a linear fashion? Why do we use PWM modulation of the transistor and not the transistor in the linear fashion? In this way, because we could theoretically put here some voltage. So use the AC converter and put here a certain voltage here in the input, drive this voltage, and then get this characteristic at the output. Why don't we use the transistor in the active mode?
It will dissipate a lot of power.
Yeah, because the transistor in the active mode there will be a huge heat dissipation, huge heat loss here on the transistor, and the transistor will simply evaporate very often. With switching on and off, of course, there are also power losses during switching, but only during switching, because we lose power only here. When the transistor is switched on and off, we don't lose power because there is no current. Either the transistor is not conducting or having very low resistance, so we are losing much less current, much less power than in the linear control. But to do this, we need PWM, and to do this, we've got the output stage of the timers, and the timers we're using today almost everywhere. So the PWM functionality for driving motors, for driving DC-DC converters, for example, for converting to analog signals, because from the PWM, you know, we can, if we have a PWM signal, then we don't need a digital to analog converter. That's also one of the reasons we don't have DAC converters very popular in microcontrollers, because we don't need the DAC converters. We can use simple RC filter to filter out the switching, and then here we will have some analog voltage here at the output. Depending on the, of course, on the on the duty cycle, because the voltage will be 0 volts if there will be 0. VCC if we have constantly high state, and anything in between will generate something from 0 to VCC at the output. That's why this is really a beloved way of changing the of generating the analog voltage. That's also the reason why DACs, digital to analog converters, although available in microcontrollers, but they are not very popular. Here we have also something additional in this microcontroller: 3 channels, which are three channels which are negated, because N stands for negated, or they are written as complementary in English. So we have complementary outputs. Why the complementary outputs? Who knows? What's the sense? Because complementary means that this signal is, we have one signal this way, the second signal this way. This is negated. Positive, negative signal. Why the negative?
It's for PMOS and NMOS?
Yes, in some sense. Yes, in some sense. It's, when we drive the motor, when we go back, when we have the motor, DC motor, because this is a simple case, and of course we have the switch, so the transistor is here, the switch. So if we drive with this switch, we rotate the motor clockwise or anti-clockwise, whatever. But what if we want the motor to rotate sometimes clockwise, sometimes anti-clockwise? Left, right, or what do you want? Of course we need to change the motor, because the motor has plus and minus. Of course we need to be able to change the plus and minus somehow. And we do it normally, so if we want to, this is configuration with one switch just to make it rotating in the same direction. But if we want to make it rotate in different directions, we are using so-called bridge. So we are using a configuration like this, where we have VCC here we have a ground, and the transistors are driven in a negated signal, complemented signal. That's why we need it. Of course, you're right, it's for PMOS and NMOS, but almost right, because normally PMOSs are here and here, and MOSs are here and here. But one signal is used to drive this, the other signal is used to drive this. So the signals are driving, because this pair is either this pair is working or this pair is working. So either we have a configuration where we have this shortened, this is configuration number 1, or we have, so then the motor has plus here and minus here, or we switch in a complementary way, then this is open, this is closed. This is open, this is closed. And then we have plus here, minus here, which means that we can rotate the motor the direction that we want. For example, the motor, because this configuration, the 8-bridge configuration, is used for many, again, for driving many loads, many different loads. But for this purpose, we need complementary outputs. And they are automatically generated. They are automatically generated with some optionality in microcontrollers. Again, this is something that we have quite common. Another question: why 3 such outputs are here? More difficult question. Why 3 outputs? Not 1, complementary, but from this time we will have 3 outputs even. Has anybody any bloody idea why? 3. Not even 4, because the 4 is just single-ended, but 3. But it's for purpose that there are 3. Who has an idea? No one. Of course, this is driving the DC motor such a way, because DC motor has just one winding. But today we are using mainly, they are called direct drive motors, but they are today PMSM or BLDC motors. They have in common that they are 3-phase motors. They are all 3-phase motors. Because, of course, everybody knows, I think, or maybe, standard three-phase motors that we can supply from the from the AC mains. But in digital world today we're using direct drives, which are basically the brushless, so-called brushless motors as well. They are in fact three phases, and they need three such pairs, 3 H bridges to be driven. And microcontrollers today support it directly. So we have a timers with 3 such outputs that we can connect 3 bridges and drive such a PMSM motor directly from a microcontroller. That's also the reason why we have 3 outputs here. Yeah, in microcontrollers, and that's also the case here in this microcontroller. We can quite often choose the source of the clock count going to the prescaler. So this is again CK/PSK. This is the clock. Take a look here. I mentioned about it that it's sometimes a guess game. What is connected and what's the frequency? Something that we have to really be very careful about. Why? Because take a look. This is the circuit just for connecting what is connected to CK/PSK. And normally the default one is this multiplexer. It is. Take a look from this chart. We can read directly which register and the bits in the register, because this is the register TIM1 register SMCR. So if you want to modify it in the software, you just open such a chart and you can read from this chart which register, which bits in the register modify the particular multiplexer. So these bits change this the inputs. We've got the master. So this is the standard clocking, and that's not that easy. Then we have to find how the master is generated and what's the frequency of the master, because it doesn't need to be FCPU. It's usually, there is usually some divider that we can set. But then we have external clocking mode. So this signal, we have the trigger signal that comes from either from other timers in this case, or just from pin. So we have pin, we have filter, we have some edge detector, and then we can connect it to this pin and we can count it. Yeah, maybe we'll not analyze everything. I'll just to point this nice extension. This is so-called encoder mode. Feature that is not always present, but quite useful it is in practice, especially for BLDC and PMSM, but not only for that. In case of encoder mode, if there is such a case, then we can. Encoder mode means that the timer automatically counts this kind of signal. What's this? This kind of signal. This is encoder signal. Encoder, it's something that, for example, rotates, or there is a linear scale, and we are measuring the shift along the scale, or the rotation, how much it rotated, how much was the angular rotation, or the speed of rotation, whatever. In general, the encoders are delivering this kind of signal. We call it signal in quadrature. So these are signals in quadrature because they are shifted of plus minus 90 degrees. What's the sense of it? If we rotate, for example, clockwise, then the shift is plus. If we rotate anti-clockwise, then the shift between those two signals is minus 90 degrees. And this changes in, so on both signals, the edges, they mean about how much it rotated. So the phase shift between signals tells us about the direction of rotation or direction of movement, while this, the amount of, the number of edges of clocks here tells us about how fast it rotates or how fast something is moving. Because, for example, one transition could mean, let's say, 1 micrometer of movement. This kind of encoders are quite popular in the industry, and it's very nice if a microcontroller timer has is supporting this kind of functionality. Okay, maybe let's skip some functionality, because the functionality of the as you can see, this is just the STM8, so the functionality is still limited comparing to STM32, for example, or other 32 bits, but still plenty of elements that you can find here. Here is the input stage, how it looks like. So we've got the filter. Take a look. There is an input. There is a special filter filtering the input, signal, plus the edge detector. Choosing the rising or falling edge, and then even additional divider, and only then it goes to the input capture. In case of the output, we've got the from the counter. Then there is something like that time generator and many other things that generates those negated complementary output. So maybe we'll skip it for now. Maybe we'll skip it for now, as we don't have, unfortunately, time to analyze everything. Or fortunately, maybe depends on you. An example of how the PWM can look like. You can see on the slides with various duty cycles. So 1/8, so one part of 8 is active, 2 parts of 8, and duty cycle 6 parts of 8. For example, like this one, of course, 8 of 8 will be 100%. In case of duty cycle, in case of PWM signals, we have to know about 2 various parameters of the signal. So the duty cycle is one of the parameters. Second one is the period. The period, so the frequency of the signal. So the duty cycle and the frequency can be also, and the third one is resolution. So how fine can we set the duty cycle? Here in this example is the resolution just 3-bit, because we can have 8. We have just 8 states that we can choose, 8 possibilities we have for the duty cycles. The higher the resolution, generally, the better. Also, the higher the frequency capabilities, generally, the better. Maybe let's keep it this way. It's possible in case of timers also for 1 pulse mode to generate just 1 pulse, so that we generate a pulse depending on some functionality. Here is an example that we have an input to a microcontroller of any shape, of any length, and it generates a dedicated output. This is so-called monostable functionality. We talked about it last semester. So with monostable generators, which are just generating 1 dedicated pulse width. Sometimes it is necessary in some applications that we have, for example, a user, human being, presses a button, so you can press for a short time, you can press for a very long time, and out of this, it is to be generated a pulse of dedicated width to drive something, to open some window, for example, or drive a motor, whatever. This kind of functionality we can have, but here is a functionality coming from the input. Here, naturally, this one pulse mode can come from another, from an application, from a microprocessor, from some peripherals into microprocessor. An example about the encoder input mode, and as well why the encoder input, because this type of quadrature signal was. The bad thing about the quadrature signal is that it requires special decoding. If you want to use encoders in your applications, you must have a microcontroller with a timer which supports the encoder input. Because decoding the encoder part, decoding this quadrature signal without a special dedicated timer is very time consuming for a microcontroller. Because it's a stupid thing, but takes really a lot of resources without a timer, dedicated encoder input timer. But this signal is really a strong thing. The good thing about this, it's used in the industry not only because it gives us the direction of movement, because we can have, depending on the phase shift, take a look, phase shift plus 90 degrees, minus 90 degrees, forward, backward, but also because it's not sensitive to noises. Here it is called jitter on this slide, but these are actually noises. And here it is the here is the width of this pulse is wide, but we talk here about pulses like this, about the such spikes. those spikes are not recognized by the encoder input. Normally, take a look, if we will analyze such a signal normally, we would count them up. We would include them in the final result. But for the encoder tape signal, they are just excluded because formally, if such a spike like this happens, this is calculated plus, this is minus, +1, -1, so this is 0. In a single lane signal, it's counted always. So the encoder inputs, if we talk about robots, if we talk about machines, the encoders are always present, and the encoder interface. But not all microcontrollers have dedicated timers with dedicated encoder inputs. So here, something that you should take it into account when you want a microcontroller to be used in such applications. Another application where interesting one in case of microcontrollers is synchronizing the PWM. So it doesn't look like, so here we have a situation that we have sample situation that we have one PWM driving some DC-DC converter, another PDM, another DC-DC converter, another one, another DC-DC converter. Of course, theoretically, it's possible then each DC-DC converter works independently. That's the simplest possible operation. So no synchronization is here switched on. What is happening then? Then if there is no synchronization, then switching happens at random times because each DC-DC converter in this example works differently, which means that current switching occurs in various times, which of course means that we've got spikes. We've got various spikes, current spikes or electromagnetic interferences occurring constantly or randomly at random times. And for example, to avoid this, we can synchronize. We can synchronize everything. It is possible. We can synchronize we can switch on the synchronization here, and we can synchronize the converters, for example, the power switching between the timers. And thanks to this, it would be possible to avoid, because the problem is if we want to make the ADC conversion, here in this example, it's not possible to convert anything because we never know when the switching will occur. In the synchronized, and that's why we synchronize the timers, we are synchronizing it to know exactly when the switching will occur. Then we can avoid the, we can convert, we can, for example, make precise ADC conversion, not here, but exactly if we know that the switching will be here, then we can do it earlier or later. That's the way how we avoid today in microcontrollers the necessity. We talked about the linear and switching power supplies. This is one of the methods how to be able to use switching power supplies today in microcontrollers, even if there is required a very low noise or very high precision of conversion. So we are switching, but we are switching at time t1, and we are converting always time t1 plus epsilon or plus some delta. That's how we do it, and the synchronization is actually the reason or the method of doing this. Yeah, an example how bridges, how to control it. But again, curious of what I wanted to show you. An example, the PMSM motor. So three-phase motors, the connections of three-phase motors, and why we need three outputs, why we need the three dedicated complementary outputs. So that's how we connect the PMSM or BLDC or in general three-phase motors to a microcontroller. So then we have to drive, of course, PWM signal here, PWM signal here, PWM signal here. But this gives us the powerful direct motor drive, so-called direct motor drive, very popular today. Those direct motors replaced AC motors today, very much. So if you go, you want to buy some home appliances like washer, for example, washing machine. Mark that machines with the AC motors are much cheaper than direct drives, but cheaper, not much, because in the past, a few years ago, the direct drives were very expensive. They were very expensive because they required DSP processor, and this was complex and expensive. Today, and AC motors were cheaper because the motor was simpler. Today, because the microcontrollers, like this exemplary, have everything included, everything inside. So we just one microcontroller, we just need this kind of bridge. This is just single chip solution today. And then we connect a high current motor, and then we drive it directly. That's why the prices drop. Of course, those motors are more reliable, and comparing to AC motors, more reliable and lighter, and we can control it better. Okay, maybe that's it. We just have 5 minutes, so just the beginning of interrupts. To proceed, the interrupts, the basics of the interrupts. Why do we use interrupts? Maybe let's focus today on this one, the rest one later. Of course, everybody knows what is an interrupt. So interrupt is that we have a normal application flow, then we have an interrupt, so we stop our main code, we interrupt the interrupt service routine is then executed by the CPU, and then we get back. So why do we use interrupts? First thing, because they are the simplest multitasking. So they give us a chance to have different applications running in almost the same time. So this is of course we call it preemptive multitasking, because the application. So here this is the application. So they preempt the current application. We can also make a nesting in case of interrupt. So we can make another interrupt service routine of higher priority, stopping this, pausing this the execution of this level interrupt service routine, and then we can force the microcontroller to execute another service routine, or we can make some small list of interrupt service routines that will be executed. Many options we have, but still, this is the simplest multitasking. Another second argument for using interrupts in microcontrollers is that they simplify programming. They simplify programming model. We do with interrupt service routines, we put this here, the time critical code. That's how we do it normally. So we put time critical code. What is not critical, we put in the normal flow. Here we put the things that must be done after something happens, so after an event occurs, or after a special time. So in general, doing it in a linear way, it's possible, but with interrupts, it's much simpler. Because it's an easy way for communication between peripherals and CPU. Again, we can, with interrupts, if something happens, if something occurs, for example, if a conversion finished in some ADC converter in the peripheral, naturally the CPU may ask if it finished, so may test the status. We call it may poll such a peripheral. So this polling is possible, but polling takes time, because polling, microcontroller has to poll, has to have time for checking the status. With interrupts, it's naturally way simpler, because with interrupts, we just, the microcontroller does its stuff, and then when the particular event happened, then we've got the event being serviced and executed. And naturally, all this is because we get higher performance. That's why we use interrupts today, and we use them very extensively. Really, my beloved example are the microcontrollers from today, comparing to the microcontrollers from the past. In the past, the microcontrollers tend to have 3, 4, 5x interrupt sources. Today, we talk about a few thousand interrupt sources in one microcontroller. So we can service an interrupt coming from a few thousands of various events happening within the microcontroller, peripheral, internal, external pins, state of the microcontroller, many things. So the interrupts are really helping us to increase the performance of the microcontroller. More examples of the interrupts are made and more features of how the interrupts are working, especially on the base of STM8 already next time. Thank you very much for today. Hope to see you soon.